Hello, dear colleagues. My name is Kovalchuk. I am from Institute of Physics, National Academy of Science of Ukraine. Currently, I work in the field of spectroscopy, but I would like to tell you today about some work which I have done 1 year ago in slightly different field. So its work is about spin wave scattering on spin lengths in three-layer uniaxial ferromagnet with non-ideal boundaries in external magnetic field. This work was done in cooperation with Chernivtsi. So let's. What is the goal of my work? First is to find the analytical expression of the focal length and refractive coefficient of spin length with non-ideal boundaries. And the second is to investigate the dependence of these values from the spin from the value of magnetic field and frequency of the spin wave. And also investigate how change of parameters of interface and of mediums will change these values, such as reflection coefficient and focal length, and also express results graphically. So let's consider. Let's see what is spin length. Spin length is basically consists of three mediums, which has a different parameter of medium, different saturation magnetization. Basically, you can just make the analogy from the optics. It's basically the same, just medium is magnetic. So to find these values such as focus length and reflective coefficient, we need, of course, to find the rules of dynamics of the spin waves in these mediums. So for doing this, we used quantum mechanical approach. Sorry. I don't see here laser. Okay. So here you can see standard equation for which describes behavior of atom with magnetic moment in magnetic field. Here is effective magnetic field, which we found by this formula, where is density of the energy described as following. Here is A alpha is a parameter of exchange interaction in medium, and beta is parameter of uniaxial magnetic anisotropy, and here is external magnetic field H. So the solution of this equation we found as in this form, whereas first part describes the main state basic of the magnetic moment of atom, pointing in the direction of external magnetic field. And the second part describes some fluctuation from this main state. But basically, it describes behavior of precession of spin. After we put this, after we put solution in equation, we can find the equation of the dynamic of magnetic moment, which gives us the dispersion equation, sorry for grammatical mistakes, in this form, which gave us the possibility to use a geometrical optical approach to find the focal length. This standard formula from optics from which you can find the focal length. Okay, so the next part of work was to find the reflective index, reflective coefficient. So to do this, first we tried to find good boundary condition which describe behavior of spin waves the interface. So it was done using standard equation of behavior of magnetic moment in the external magnetic field. Energy density was presented in such form, which as a result we obtained such boundary conditions, whereas A is parameter of exchange interaction at the interface between two mediums, and sigma basically describes inhomogeneity of anexial magnetic anisotropy. On this graph you can see how these parameters change with changing of x coordinate. You can see interface, and you can see that at the interface parameter of interface is constant, and the same for mediums parameters which constant like in the medium. So after we found boundary condition, we use standard quantum mechanical approach to describe the spin wave in each medium, whereas in first medium spin wave described by this equation, whereas first part describes spin waves which fall on the interface, and the second part is spin waves which reflected from the interface. And the same for the second medium. And for the third, we have just spin wave which go through medium. Okay, so after we put solution in this form to the boundary condition, we get a reflection coefficient in this form. Basically, it was really massive, massive formula which depends on. You can see a lot of parameters. I just simplify it a little bit. So let's see how graphically, on graph, how dependent on the dependence graphically. So here you can see the dependence of reflection coefficient on frequency and magnetic field. Here you can see some peaks, which is due to which is due to interference from two waves. First waves is waves from the which is going through second interface, and the second wave which is reflects from the second go to the first, then go back to the second, and the interferes here, and we can get such peaks. This point is point of full reflection of spin waves from the spin length, and it is due to the fact that at these values of external magnetic field and these parameters of mediums, we get just a complex vector of wave vector, which lead to exponential decrease of spin wave in third medium. So we just have full reflection of spin waves. Okay, here you can see the dependence of the reflection coefficient on frequency and external magnetic field at different values of coupling parameters. It's parameter of exchange interaction between two mediums. From here you can see that at a relatively big value of these coupling parameters, we haven't such distinguished peaks, but with decreasing of these parameters, we have really big interference peaks, which is at first graphic really becomes really intense, and the next is dependence of reflection coefficient on frequency and different values of parameters of exchange interaction. So here you can see the same pictures with interference peaks and point where you can get full reflection spin waves from the spin length. So as a conclusion, I want to say that in this work we obtained the focal length of the spin waves and the reflection coefficient, and found that these values extremely depends on the parameters of mediums and parameters of interface, and also of the external magnetic field and frequency of spin waves. The results of this work can be applied in spin wave electronics, I think. Okay, thank you for your attention. If you have questions, please.
Equation
okay. Okay, thank you. Okay. Yeah.
So, as far as I understood, is a theoretical.
Yes, I should mention it from the start. Yes.
As far as I know about electronics and speed and so on, where speed lengths could be used?
As I said, it can be used in some.
So there are speed walls or some schema lenses where is in the future.
Actually, it's like more questions of imagination where you can, and creativity, I don't know.
Probably very far future. Okay.
Of course. Thank you.